Hi, in this step-by-step tutorial, we will create a Boids Flocking Simulation using Three.js with React 3 Fiber. We'll be implementing this simulation using fish, but feel free to get creative and experiment with any other elements you prefer. Before we begin, for those new to 3D web development or who might have questions during the project, my project-based course React 3 Fiber, the ultimate guide to 3D web development, provides the perfect foundation and detailed answers. Link in the description. Let's start by cloning the starter pack I prepared for you. Click on Code, copy the URL, link will be in the description. Then in a terminal, run git clone, paste the URL, and I will type the folder name I want to put it into. Then we can open the new folder. To run our project, we need to install the dependencies with yarn install, and then yarn dev to start the development server. Follow the link by clicking here. This is what the starter pack includes. We have a simple UI with two themes, the underwater and space theme, that will change the model and the different colors. We have 8 different animated fish models that you can reuse in your project, thanks to Kirzozz, who made them specifically for this lesson. You can find the link to her socials in the description. Just to show you a last thing about the starter pack project, we have the themes that contain the underwater with some variables about the colors and the models we use, and same for the space one. This way you will be able to easily customize it to what you like. Before starting to create multiple fishes and create their movement, what we will do is create some sort of boundaries where our fishes will be able to swim. To make everything configurable in the top right, we will use controls with leva. So we create a boundaries object. We name a folder so it will be well organized on the top right. And inside, we'll have debug to true or false if we want to show it or not. We set it to true by default to visualize the boundaries. Then the X, Y, and Z values. It will limit how far we can go on the X, Y, and Z axis. Then we add collapsed to true to close the folder by default. By doing this, we can see the closed folder, we have debug to true, and we have X, Y, Z value we can change. To visualize the boundaries when debug is true, we create a mesh visible only when we have debug, then a box geometry with the X, Y, Z value of our boundaries, and a material which will be transparent and double side so we still see it if we are inside the box. This is what we have. If we zoom out, you can see we are within a box and we want to allow our fishes to only swim inside that zone. We will handle it when we will make the algorithm later, but first let's make it responsive. So if our screen is bigger, the boundaries will be adjusted to the correct screen size. First, we create a state containing the window width and height. We use a state because we want to provoke a re-render when there is a resize of the window. Then we create a scale X ratio to be able to resize it based on the window inner width and the ideal width, which is for me 1920. We use math.max to be sure we never go below 0.5 or things will be too small. Then we do the same for scale Y. And then we create our responsive boundaries. So it will be our boundaries.x multiplied by scale.x. Then we do the same for y, but using scale.y. And the depth, we don't need to adjust it. It should be fine. Now in a use effect, we will add an event listener when our window size change. We will call update size function. And when we have the cleanup function, we remove the event listener. To create our update size, first let's have a timeout. We will create the update size, and the first thing we do is we clear the timeout. Why do we do this? Because we don't want to call it too many times. So we create a timeout with a short value, and we do our set size. Let's say every 50 milliseconds. So we are sure that when we resize, we only call it, we throttle it at least 50 milliseconds. Now we can save it. And instead of using our boundaries, we'll be using our responsive boundaries. Here it looks too small because I zoomed out. Let's reload. And you can see the size is correct. If I adjust the size, you can see that the boundaries change correctly. Perfect. Now we will be able to jump to the Boids component. First, let's pass the boundaries because we will need them. We will pass the responsive boundaries. Now let's open the Boids component. Currently it's nothing fancy, but we'll make it perfect. We need the boundaries. To be able to create all our fishes, first we will need some variables. Again, we will use control from leva. We'll need the number of boids, the minimum size, the scale, and the maximum, the minimum and maximum speed, and max steering. It's how much we allow it to move and rotate. We put them in a general settings folder with the number of boids. We set the default value to 100. Then you can adjust the value to what you like and you will have the controls on the top right. And again, set collapsed to true. We will start by making our algorithm only visible in 2D, so it will be easier for us to visualize what is really happening. So let's create another control. We'll put it inside Boid rules that we name 3D. By default, we will set it to false. And that way, we will only see things in 2D. And again, collapsed to true. Now we have our different variables and controls. We are able to create our Boids array. To create our Boids, we don't want to recreate them at every render, so we'll use a useMemo hook. Inside, we will create a new array based on the number of Boids we want, and we will fill them with some data. First, the model of one single fish. It will be using one of the models from the current theme we are in. So we use runInt of 0 to the array length of our model array. So you can see for underwater, we have 7 different models, while for space, we'll be only using one. So it will always select this one. Then we assign them a random position. So we only use our boundaries, a random float of minus boundaries.x divided by 2. So the absolute left, or the absolute right, and it will take a position in between. We do the same for the y and z axis, but we have our control. If we are not in 3D, we will use 0. Otherwise, we positionate it randomly on the z axis too. Then to be able to move our fish, we will need to have a velocity variable. We'll have a wander variable. I will explain it to you right after when we will start the algorithm, and the scale to size it properly. Then for our useMemo, what will trigger it? The recreation of all the boids. So we pass it in the dependencies array. It will be the number of boids, the boundaries if they change, the theme, the minimum scale, the maximum scale, and if we are in 3D or not. Alright, so now instead of rendering only one boid manually, we will loop through all our boids. So we will return boids.map. We'll have boid and the index in the array, and inside we will render a boid. We don't need this anymore, and we can assign the different variable. First, we need a key. We'll use index and we will add the boid model. So if it changes, it will recreate a new boid. Then the position, we have it inside our boid. Same for the model, boid.model. We also have the scale and the velocity. We could also do this, but it's less practical to visualize exactly what we pass. If we save, this is what we have. We have different fishes within the boundaries, and they are different. They have different scales and different colors. The first step to implement our flocking Boids simulation is to make them wandering. What it means is they will go randomly in any direction. Let's say we have one fish. Imagine it is a fish, and we just want it to go randomly into a direction. Let's say it can be forward, turn on the left, or turn on the right. To easily achieve this result, we will draw a circle around our fish, and with the variable we created earlier, wander angle, what we will do is If it is 0, it will point at a certain direction, and if the value increases, it will be another point on the circle. Then if it decreases, it will be somewhere else on the circle, and our fish will target this position on the circle, so it will rotate smoothly in the right direction. It will be wandering. To start creating our algorithm, on top of our component, we will declare some vector 3, because we don't want to declare them at each frame. The first one we need is the wander force and the steering. It's what we will apply to our velocity by combining different forces, such as the wander. Let's head back to our Boids component, and we will add some controls to fine-tune the effect. We will want to have the wander radius, it's the circle around us. The strength, it's the strength of the wander we will apply on the steering. Currently we only have one, so it's not important, but we will see later when we combine different forces. And the wander circle, it's just a debug control we will add to visualize the wander radius. Let's create them. Use controls, wander, so it will be in a folder. Wander circle false, the radius, and the strength. We set it to 2, but again, it has no importance yet. Then collapsed to true. Let's start by doing this wander circle debug. We go on the Boid and we pass the two variables. So wander circle, if we display it or not, and the wander radius. We divide it by the scale so we can correctly visualize the size. Then we add it on the props of our Boid, and we simply add it here. So if we have wander circle, it will be visible. It's a sphere geometry with the radius of our wander and a red wireframe material. Let's visualize it, wander circle, but because there are too many, it's difficult to see how far we go. So let's add maybe 2 Boids, enable wander, and here you can see this is the radius we will try to wander around. All right, I think we can debug using 60 Boids. Let's start to create the wander algorithm. In a use frame, we will need the delta, the time between frames. Then in a for loop, we will loop through all the Boids, and we will get the current Boid we are on. To wander, what we need to do is to increase our wander variable on each Boid of a random value, so negative or positive. Then we set our wander vector. We use the cosinus and the sinus to get the position on our circle defined by the wander radius. We use 0 on the z-axis, and then we normalize because what interests us is just the direction. And then we multiply the scalar of our vector by the wander strength. So the higher the value, the higher it will be impactful based on the different forces. Currently we only have wander, so you won't see a difference. Now let's apply the wander on the main steering force. First, we need to reset the steering because it's a global variable we have here. We want it to be at 0 at the beginning. Then on it, we apply our wander force. Then to prevent them to turn too much, we clamp the length between 0 to max steering multiplied by delta. This way, it will never go above the max steering value. Now we have limited the steering value, we can add it to our velocity. And because we don't want our Boid velocity to go above the max speed, we clamp its length between 0 and max speed multiplied by delta. And finally, we can apply the velocity, which is the speed and movement of our fish, on our position. So simply Boid.position, add Boid.velocity. If we save, nothing happens. It's because we are not using the velocity and position inside our Boid component. First, let's add the velocity on our Boid. Then in a use frame, we'll create a target. It's where our current Boid will look at. We are using our current group and clone it to be able to lerp the rotation. So we do target.lookAt, we take our current position and we add the velocity to it. So we will look towards the direction we are facing. Then on our current group, on the quaternion, we will lerp its value with slurp and target.quaternion, which faces the value we want to lerp towards. If we save, you can see they are rotating towards the right value. And then what we need is to copy the position to be equal to the one we have in data. If we save, it's working, but we have an issue because they are not respecting the limit, so they go anywhere. So the simplest solution for the limits of our boundaries would be to simply check if our position is over, then we will teleport it at the other side. So if we are too much on the right, we teleport to the left. And we do the same for the left, we go to the right. Same on top and in front or backwards. Well, let's try it. It works. You can see they are teleporting from one side to another. But this is not the effect I want, because I want to have a floor, I want it to be realistic. So instead, the solution we will apply, but if you like this one, you can keep this one. What we will do is we will apply a negative force to avoid the boundaries. Let's add the ground so you can visualize why it's an issue. Go to experience. Now we have the boundaries, we can do it. And we create our ground. We create a mesh with the position y, which will be the responsive boundaries of y divided by 2. So it will be the bottom part we see here. Then we rotate it, we receive the shadow. And we create a large plane with the color of our theme. If I save, let's make it a bit bigger. You can see we have the shadow, but then it's going inside the floor, which looks not so good. Let's go back to our edges here and remove this algorithm. We will need a new force. Where do we define them? It's here, global them. So we'll call it limits, where we reset our forces. We do it too. Limits dot multiply scalar of 0. So it's set every value to 0. Let's apply our logic for the limits. If our position plus 1, a threshold, it goes above the boundaries, then our limits dot x will be the opposite of our current position. Then if we are wandering, we will apply 180 degrees, so it will go the opposite way to start wandering in the correct direction. We do the same for the y and z. So the limit vector will be a force to push us in the opposite direction. And we just change the wander to be sure we are changing our current rotation, because it seems we are not going in the right way. Then again, we normalize our vector and we multiply it by the strength we want. We make it very strong because we never want to go out of bounds. Then we simply apply our limits to the steering. And now you can see they are always within the limits, and when they almost reach the boundaries, they go back to the opposite direction. Maybe the current size is a bit too small for that many. If you start to have some background noise, I'm sorry, it's the typhoon outside in Japan. Before adding other forces, one last thing I want to do is to adjust the speed based on the size of the fish. Currently, we are only using the max speed, but we defined in the general settings a minimum speed. What we will want to do is that if you are a small fish, you go to the max speed. And if you are a big fish, you will use the min speed and everything in between. To achieve this result, we will use the remap function. What it does is it's taking two values, so 0 and 1, our current value between those two, and remap the possible value we have between two other values, between 0 and 2. Let's zoom to see what we have. So if we have something below 0, it will be equal to 0. If we have something above 1, it will go to 2. And anything in between will be adjusted. As it will be a bit the opposite, because if we are small, we want to be fast. So it will be 2 and 0. So if we are small, it will be using the maximum speed. And if it's big, a higher value, it will use a minimum speed value. I found the remap function online on Stack Overflow. And you have the value low, high input, low to and high to the output. So here, instead of using the max speed, we will use the remap based on the scale of our Boid between the minimum scale and max scale. And we will use the max speed, which will be for min scale, toward the min speed if we are the bigger. We save. And You can clearly see that here it's a small one, it's going pretty fast, and the bigger ones are a bit slower. Now it's time to make our flocking Boids simulation. It lies in three principles. Alignment, which is when you have other fishes, you try to go in the same direction. Separation, it's when you are too close to a fish, you try to go in the opposite way to avoid it. And cohesion, to try to go in the same position than the other fishes around you. It creates nice patterns. Don't worry, we will see them step by step. We will start with alignment. Let's say we have another fish going in the opposite direction, while we are going into its direction. We will take the velocity of all the different fishes within a radius around us, and the further it is to us, the less it will impact us, but the closer it will impact us more, and we'll go into an average direction. So both of them will try to go into the same direction. We can create a new force, we'll name it alignment. Inside our Boids rules, we will add alignment to decide if we want to enable it or not. And we create some controls with the align radius, how far around us we try to align with the other fishes, the strength, and the circle to visualize the circle or not. Inside our algorithm, first let's add the new force to the reset forces. Now below the limits, we will create our new algorithm. Because it is based on the other fishes, what we need to do is to loop through all the other ones. So currently we loop through all of them, but if it is our current fish, we continue, we skip this one. Then we get the other Boids. Because we decide to apply alignment only if a fish is near to us or not, we will need the distance. We simply call distance 2 of our position to the other position. For the alignment, we need to check if we are within the circle around us. Then we get the velocity of the other fish. We normalize it because we only want to know its direction, and we divide it based on the distance. So if it's far from us, it won't impact us much, but if it's close, we'll be very well aligned with the close ones. Then we add this strength from one fish to our alignment force. Then, where we apply our different forces, we will add the alignment. We check if we enable the alignment inside our controls. We normalize it because we want the general direction. Then we multiply it by the strength. So it will be either more wandering if wandering is stronger, or if align has a higher value, it will do more alignment than wandering. And we add that alignment force to our global steering. And we can save. Now you can see they are aligning. It's a bit chaotic because it's a very small space, but you can see that they are both wandering because there is this force, but also they are aligning in the same direction. To adjust the different parameters, you can add the align circle and align radius, add it to one fish, and to create a mesh to visualize it. Let's go to alignment and enable the circle. So you can see they have a large zone around them. If you want it to be smaller, they won't align that much because they will only align with the one in that circle. Perfect. Now let's head to the second algorithm. We have seen alignment. Now let's add some separation. There are one or multiple fishes and we are going to collide. Again, we will look around us, maybe a smaller zone. So if it is inside, well, currently it's not. Let's say we are in the circle. We will subtract its position to our current position, which would bring us here. And we will go in the opposite direction. Of course, if there are multiple fishes, it will be an average, but globally, it will avoid the other fishes. Let's apply it. We create a new force named avoidance. We create a new rule here, avoidance, if we enable it or not, named avoidance. And then some other controls. It's exactly the same. A radius, a circle, and the strength. We can directly add the debug on the Boid and display it if it's enabled. Now in the use frame, we need to reset the force of the avoidance. And because it's related to the other Boids as well, we can put it just below the alignment. Okay, so again, we check that we are inside the minimum distance to apply avoidance to other fish. Then we calculate the difference between our position and the other position. So actually it's the opposite position. Then we normalize it, and like we did before, we divide by the distance. So if it's far from us, it will impact us less than if it's very close to us, because we want to avoid the ones that are closer to us. When I say to us, I don't identify as a fish. And let's apply the force. First, we need to check if we have avoidance. If we do, we normalize it. We multiply by the strength of avoidance, and we add it to the global steering. All right, let's see what we have. We can go in the Boids rules, disable alignment, enable the circle. So currently it's pretty big and it tries to avoid the different fishes. Maybe we can make it smaller so it will only be impacted by the one very close to it. And if we also enable alignment, you can see both acting at the same time. I will remove the circle. Okay, perfect. Now the effect is better. They are not too close to each other. All right, this time we will talk about the cohesion. I promise this is the last time I will draw. Let's draw other fishes. This one here. Let's do this one here. And a last one here. Again, we will look around us. So within a circle or a sphere when we will be in 3D, but the concept is the same. And based on all the other fishes within our circle, let's say they are all inside the circle, we will average one position that our fish will target. And because all of them will target this average position, it will create some sense of cohesion. Guess what we will do? Add a new force, cohesion. Then add the cohesion rule here. If we enable it or not, create additional controls that are exactly the same, radius, the strength, and the circle. You can pass it down to the Boid, get the props, and create the debug mesh if you want to adjust the size. Again, we reset the force of the cohesion, and because we will want to create an average, before looping through all of them, we'll create a total cohesion that will be equal to 0. It's the number of ones that are within our radius. Then let's go after our 2 algorithm and let's create the cohesion. If it is within the right distance, we will add to the cohesion vector the other position and we will increment the total cohesion we just created. Now we can go to apply forces. If we have cohesion and we had other fishes inside the radius, then we will divide the cohesion by the number of fishes in the area, and we will subtract to this vector our current position. And then, as always, we normalize it and we multiply it by the strength, and we apply it to the global steering. Let's try to see what we have. The Boids rules enable cohesion. You can see if we only enable this, they will collide too much. So we need to enable some avoidance to create separation and alignment, and then they start to act properly. By the way, it would be good to enable all rules. So far, we've only done it in 2D for better understanding of what is happening. Let's enable the 3D. It's working out of the box because we had the generation of Boids properly done if we are in 3D or not, and the different forces work. But our wandering is only applied on a circle, so it's not ideal. We need to create a second wandering force to make it 3D. As for now, the wander is only vertical. Let's make it horizontal. The logic is exactly the same that wander, but instead of applying to X and Y, we'll apply it to X and Z. Then we do the same thing because we directly set the value and not add them. We don't need to reset the forces for the wander. And then let's apply the wandering horizontal force. If we are in 3D, we do it. Let's look at what we have. It's looking way better. They are going in depth. Of course, I use different values for the strengths that I found look good, but you can adjust it. Let's say you don't want much cohesion, you can reduce it. You want more avoidance, you impact it. You will create the flow that looks good to you. But if you follow this tutorial, you know that it's not what I showed you in the intro. So now let's make it beautiful. First, let's go back to experience, boundaries, set the debug to false, reload, and we don't have those debug zone anymore. We don't want to see the fishes going backwards. So what we can do to make it nice is add some fog. So when they are further away, they will just disappear and reappear when they come back. And it creates a nice separation between the ground and the sky or the water. We can also adjust the camera position to be slightly above. If we reload so far, it's a bit better. If we switch to space, by the way, we have the other fish used. But we are still far from what I promised you, because we need to add some post-processing effects. The best place to find good-looking post-processing effect is through React Fiber documentation and look at the different example. For example, here you have God Ray. This is what we will be using on the sky. You can see that the screen is doing those nice God Rays. To add the post-processing, we need to add the library at React 3/post-processing. Once done, yarn dev and hide the terminal. Head to the experience and we will add the effect composer. Let's make it at the end of the component. Let's add the effect composer where we will put our different effects. But to add the God Ray, we still need a mesh that will be used for it. We will need a reference to that mesh. We'll name it sunref, and we'll use a state to have this reference. It's because we will want to create a re-render to pass the ref to the effect. So we create a mesh, and for the reference, we'll pass set sunref of ref. That way it will cause a re-render with the actual reference. Then we place it where we want, and we use a circle geometry and a mesh basic material using the color from the theme. This is what it looks like. We have the circle on top of the screen, and then only when we have our sunref, that's why we need the re-render, we will create a God Rays component with the sunref as the sun and with some parameters. This is what we have. That nice God Rays effect when the fishes are between the source light and our camera. It creates beautiful rays of light. Let's try it with the space, and we also have that effect. Another effect that looks good is the depth of field. We will create some controls to adjust the parameter for it. Again, you can find it in the documentation or in the examples. Focus range, distance, focal length, bokeh scale, and collapse. All our folders are collapsed. And then, based on our theme, if it has DOF or depth of field, we will apply the effect, because on the space it doesn't look good. So we will have the different parameters we created. If we reload, you can see the fishes that are too close to us or the ones that are too far from us are a bit blurry, while the one in the middle, they look sharp. Then for the space fishes, we can add some bloom so they will shine in the sky. We add some bloom with different parameters. When we want to apply the bloom, the intensity of the bloom, we save, and the effect is quite gorgeous. Then last thing we want to do is to add some floating 3D text in the middle. Again, I'm creative, but I also find inspiration somewhere. So I looked at the examples, and for the texts, I think it was this one, portal shapes. And you can see how lovely the letters appear. What makes them look beautiful is the use of the mesh transmission material from Dry library. I prepared in the starter pack a font you can use. If you don't understand how it works, refer to my text lesson inside my course. For the text, we create a group with a float component to make them look floating. Then we use the center component. Text 3D, the content of the text comes from the theme. And the mesh transmission material with the parameter we saw in the example. We do this for the title, and we replicate the effect for the subtitle. Let's save. You can see we have space word here centered correctly. But if we go to underwater, it's not centered. It's because it's not applied again. If I reload, it is centered, but then space will be wrongly positioned. This is because center doesn't apply at each render, so we need to recreate the component. The easiest way to do it is to use a key. We can make it on the theme. We save. Then if we change, it will compute correctly. But what if we resize? It will be a bit odd. So the best way is to add Scalix to the key, and that way it is responsive. By the way, note that I used Scalix to position the text and to scale the font size. Here are some ideas if you want to go further on this project. You can add some conditions to apply cohesion and alignment only on same color or same size fish. Pick different size for different models, avoid objects and not only boundaries, and ultimately perform the algorithm on the GPU and boost the performance with GPGPU. Link in the description for an example. Thank you for watching, I hope you enjoyed this video. Please hit the like button to help this channel be more visible to other creative developers. Don't forget to subscribe to not miss my upcoming tutorials. If you want to continue your 3D web development journey, I recommend you watch this video, available here.